Park. But what we've done over the past few years is also work on a specific time period in geologic history, and some of the best records of that time period are from the Channel Islands. And that's what I'm going to talk about tonight. And first of all, can everyone hear me okay? Okay. And possibly if we could maybe get some of the lights off here. Is that possible, Bill? That one's okay, but maybe some of these? Is that okay for everyone? Not too dark? No one's going to fall asleep? No. Can't guarantee that, I guess. Okay. But I'll do my best. Anyway, what I'll do tonight is talk to you a little bit about what we've been finding out for this particular time period in geology. I hear a lot of talk about how things might get even warmer in this interglacial period, and the fact that things are getting warmer. In fact, in U.S. now, as you can see, so did the glaciers up here on the Canadian islands, in southern Alaska and in the Brooks Range. And then also that little ice cap called the Barnes ice cap here expanded all the way down over most of Canada and into the northern tier of states in the United States. So the cities of New York, Chicago, and so on were all under about 3,000 kilometers of ice. Just about, well, not quite 10,000 years ago, but about 14,000 years ago. And then it started receding back, and most of it was gone a little less than 10,000 years ago or so. So that when we talk about a glacial period, this is what we're referring to, is this extent of ice over North America, and a similar kind of extent of ice over Eurasia as well, particularly in northwestern Europe. What's called the Fennoscandian ice sheet was the main expression of the last glacial period there. But mountain glaciers expanded too, in the Alps and other mountain ranges as well. And Antarctica expanded a bit as well. So we see ice growth in a lot of the world's continents. Yes, sir?
Can I just clarify, did you say 3,000 kilometers thick?
3,000 meters thick. Yeah, not 3,000 kilometers, no.
Okay,
Sorry, if I said
meant
kilometers, yeah. Yeah. And maybe more, actually. Okay. So, where did we get all this moisture to grow these glaciers? And this is a simple cartoon showing kind of what the cycle is. Most of the moisture that falls on continents, whether it's rain or snow, is ultimately derived from evaporation over the oceans. Forms clouds, moves over to the continents, falls as snow, and if summers are cool enough, it builds up an ice sheet. And because of that loss of moisture from the oceans, sea level will lower. It won't lower if we melt all that snow in the wintertime, because it just goes right back to the oceans. But if it persists over the summertime at high latitudes, builds up and forms an ice sheet, then sea level is going to lower. Has to. Okay? And during the last glacial period, sea level lowered by as much as 120 meters, so that the northern Channel Islands were all connected into one big super island called Santa Rosa. And so it was a large, large island, and similar kind of thing happened with a lot of other island chains around the world. In the Galapagos, for example, a lot of Mediterranean islands, and so on. And Asia and North America were connected at that time as well, up in Alaska. A place called Beringia is what that region is referred to as. Okay, so if we look at this kind of simple cycle then of moisture from the oceans, forming clouds, moving over the continents, forming ice sheets, and so on, we're going to complicate that just a little bit. And we're going to talk a little bit about something called oxygen isotopes. Now, water is H2O, right? So there's an oxygen in that water molecule. And it turns out that there are three naturally occurring isotopes of oxygen. And they have atomic masses of 16, 17, and 18. So the two with the greatest difference are 16 and 18. They're both the element oxygen. Chemically, they're the same, but they have different numbers of neutrons. And so oxygen 18 is heavier than oxygen 16 by 2 mass units. Everybody with me so far? Okay. What that means is that when evaporation of ocean water takes place, it happens to favor the lighter isotope. It's easier to evaporate a lighter isotope than it is a heavier isotope. Okay? So when water evaporates from the oceans during any period of time, glacial or interglacial, it favors the light isotope, oxygen-16. So the moisture in the atmosphere will tend to be relatively enriched in oxygen-16, and the ratio compared to seawater, come back. There it is. Compared to seawater is going to be relatively low, oxygen-18 to oxygen-16, because it's O16 enriched. Okay? And the oceans will be relatively enriched in oxygen-18, so its ratio of oxygen-18 to 16 is relatively high. Okay? Everybody still with me? You all pass Isotope Geochemistry 101 with an A. Okay. If we move this air mass then with all this low oxygen-18 to 16 ratio water over to the continents, have it fall as snow, and form a glacier, it's also going to have an O18, O16 ratio that's relatively low. Okay? And if that keeps happening, okay, then the oceans are going to get more oxygen-18 enriched and have a higher O18, O16 ratio. Okay? Now, why is that important? The reason that's important is that these little guys, Foraminifera, which are microorganisms that live in both the upper part of the ocean, planktonic forms, and deeper part of the ocean, or benthic forms. And here are two examples. And can everybody pronounce this? Can anybody pronounce it? A lot of times they just refer to these guys as G. sac or G. ruber. So marine micropaleontologists can't pronounce it either, so don't feel bad. But at any rate, they're composed of calcium carbonate, CaCO3. And they build their shells out of seawater. So they take the oxygen and the calcium from seawater. And so they record what the oxygen isotope composition of the ocean is at the time they form their shells. Okay? Make sense? They record that very faithfully. Now, what happens then is those little forams die and accumulate on the ocean floor, and here you can see, keep losing this thing, the ocean right here, ocean surface, and as they die and fall to the bottom, there is a pile of sediment that builds up, and if we take a core through that sediment and measure the oxygen isotope ratio, we're going to see a series of interglacials like the present one. Like the present one, a glacial period like this, which corresponds to the last glacial period, and an interglacial period before that, which is the last interglacial period, and so on. Succession of these things as we go down through a core. And what paleooceanographers do is plot these things up, and don't worry so much about this series of numbers here, but this is a kind of a normalized or averaged out oxygen 18 to oxygen 16 ratio. And what we're looking at here is an interglacial sort of signature with the large negative numbers, and a more oxygen O18 enriched glacial signature with the positive numbers here. Okay? So what you're looking at with this zigzag pattern is a series of interglacials that are high points or peaks on this graph, and glacial periods, which are these low peaks down here. And what we've got plotted down here is the age in thousands of years before present. So the last interglacial period was just a little over 100,000 years or so ago. The last glacial period, when it was at its absolute maximum, and Chicago and New York were covered with ice, was at about 20,000 years ago. Okay? So that's a typical kind of oxygen isotope curve. And exactly this kind of curve has been developed not far from here in Santa Barbara Basin. And Jim Kennett from UCSB has done some of the best work on getting very, very high resolution records because there's a very high sedimentation rate there of this latter part of this oxygen isotope record. So the oxygen isotope record in the forams then that is recorded in these zigzags is a record of glacial and interglacial periods that have taken place on the Earth over the last 2 million years or so. It's a remarkable record. And this was something discovered early in the 50s by Cesare Emiliani at the University of Miami. It's a breakthrough in geology to see this kind of a remarkable, very complete record. Okay. So when was the last interglacial period, and how long did it last? We mentioned that it was a little over 100,000 years or so ago. The question is, in more detail, more precisely, how long was it? Looks like our pointer is working again here. So the last interglacial is this peak right here, and then we had some periods where it was not really a full glacial, not really a full interglacial, and then it kind of dropped down to a glacial period. And then we had kind of a short period of relief, and then a real glacial period down here. But the last interglacial was this period right back here, around 120,000. But let's expand this part of the graph right here and look at it in a bit more detail. Oh, okay. Thank you. Okay. All right. Very good. Thanks. So here's our last interglacial period. Okay. I'm going to use that one right now. Okay. There we go. There's our last interglacial period. And using a variety of techniques to approximate this time scale, paleoceanographers have estimated that this period of time, when the last interglacial was truly an interglacial period comparable to the present one, to have been a short warm period of about 5,000 years, from about 126,000 years ago to about 121,000 years ago, something like that. About 5,000 years long, something on that order. Now, we mentioned that the last glacial period ended about 10,000 years ago. But sea level, which is mainly what this is tracking here, remember, really didn't get up to its present levels until about 5,000 or 6,000 years ago, something like that. Okay? So really what we're talking about is a period of time, a short warm period, that lasted about as long as the present interglacial has in terms of worldwide sea level. Okay? That make sense? Okay. So that's an approximation based on a series of different techniques to kind of estimate what this whole set of curves going way back in time is due to. Some of this is done by using paleomagnetic reversals and estimating what the sedimentation rates are. Sometimes it's volcanic ash. And some of it is based on calibration with what we think is what the major cause of glacial interglacial cycles might be. And I don't want to get into that too much tonight because that's a whole separate topic that if in the question and answer period, if someone wants to ask about that, we can talk about it. But at any rate, it's an approximation. That's the important point to try to remember here. And that approximation indicates a relatively short warm period of about 5,000 years. Okay. But there are other ways to get a record of that last interglacial period, and that's what I want to talk about tonight. Here's one of them, and that is to look at this kind of thing, which is the Waimanalo Limestone. That's all this white stuff that you see here. This is a fossil coral reef from the last interglacial period on the north shore of Oahu. And it's sitting here, has a lot of coral reefs and coral reef heads that are actually in growth position, same way that they were living, or positioned when they were living, and beautifully preserved like this. In other parts of the world, such as Bermuda, we don't have a record of coral reefs, but we have coral-bearing beach and shallow water deposits. In this case, it's something called the Rocky Bay Formation. And that's this stuff right here. It's a bunch of cemented sands. It has some corals in it, but it's not really a reef rock per se like the Waimanalo Formation is. But it also has a series of sand dunes that developed not too far away from that beach. And it even has an older formation called the Belmont Formation that's about 200,000 years old that dates from the next glacial or next interglacial period prior to that you saw in that diagram of the oxygen isotope curve. So this is a nice record from the Atlantic, just off of North America, of that same time period. The Florida Keys have a superb record of the last interglacial. In fact, the Florida Keys are of last interglacial age. Basically what the Florida Keys are, and here you see the upper Keys right here, and the lower Keys down here. The Florida Keys, at least in their upper part here, are a last interglacial coral reef tract. And there are, again, like the Waimanalo Formation in Hawaii, they are a series of coral reef rock sediments that have been cemented together and corals that are in growth position, beautifully preserved. And you can see them at places like Windley Key, where we've dated them at about 127,000 years, and Grassy Key at about 130, and Key Largo at about 127,000. Where Bogey and Bacall had their wonderful heyday. Let me go back one step. You can also see the modern coral reef tract off Florida. It's about 5 miles off the Keys, right across through here, okay? Just below modern sea level. And the main part of the fossil reef tract is very much parallel to that right along through here, but above water. There's Windley Key. Here, this coral reef rock is referred to as the Key Largo limestone. Bogey and Bacall would have approved of that. There's Florida Bay over there. So you can see that this is above sea level, and this is exposed at Windley Key Quarry, Florida, which is actually now a Florida State Park. So you can go visit that and actually walk through and see coral reefs and corals in growth position, like this brain coral called Diploria right here. This is on Windley Key, which I think we ought to make part of Channel Islands National Park. But no one's accepted that proposal yet. In California here, we don't have coral reefs because we're too far north for those to grow. But we do have similar kinds of records of the last interglacial on our coastline here. And the way those are, the way they start out is as a wave-cut bench like this off the southern tip of Point Loma near San Diego. We caught it here at a really nice low tide, and you can see there's a nice flat sort of bench that's cut across these sedimentary rocks, and it has expanded inland as it has undercut the sea cliff. You can see here the Coast Guard's put a bunch of riprap to try to slow that process down for obvious reasons. But over here, where it hasn't, you can see that it's expanding inward as the cliff gets undercut. And during a period of time when we have a stable sea level, and there's time for this process to go on, we can cut a very nice wide bench here. How wide it is depends on how long that sea level is stable, how weak the rocks are, how strong the waves are, the orientation of the waves, a lot of factors. But it does take time. So it's during interglacial high stands of sea where we see this exposed, such as the present one and where it's forming right now. Now, what happens though is that if we look at this cartoon, things change as we move into a glacial period. If we look at the situation we just saw on that last slide, it's something like this. There's that Coast Guard building. It's about to go off the cliff. Here's our wave-cut bench forming in the surf zone. Here's modern sea level. And as the sea cliff retreats, this will tend to be widened. But during a glacial period, what's going to happen to sea level? We talked about ice growing on the continents. The moisture comes from the ocean, so sea level drops, right? So this wave-cut bench now gets exposed above sea level and is now subaerially exposed, or exposed to air, sitting out by itself as a mesa-like landform that we call a marine terrace. Okay? So when sea level lowers, as we move into a glacial period, that wave-cut bench gets left behind. We now call it a marine terrace. Okay? And we have lots of marine terraces along the California coast and all the way up into Oregon and parts of Washington, all the way down into Baja, and continuing all the way down on the Peruvian and Chilean coasts of South America as well. So this is a common landform on a lot of high wave energy coastlines, such as California. Now, let's put that together with that oxygen isotope curve that we showed earlier. Remember that? That same oxygen isotope curve that we showed before is right here. Here's the last interglacial period. Here's the present interglacial. The interglacial before that, this is when that Belmont Formation on Bermuda left its beach sands behind. Interglacial before that, and so on. And what else do we have going on here? And particularly in the Ventura area, where we have a lot of this going on at the present time. Along the California coast, a lot of our tectonics or earthquake generating mechanisms in the interior of the Earth are actually of a strike-slip nature, where we have things like the San Andreas Fault, where you have two masses of the crust that are sliding past one another. But there are places where we don't have quite a straight line with the fault, and in the case of the San Andreas, north of here, we've got a big bend in it. In fact, it's referred to as the Big Bend in the San Andreas. So instead of those plates sliding smoothly past each other, they actually are kind of colliding against each other, causes a lot of compression, and forms a bunch of upfolded rocks called an anticline. And you can trace the Ventura Avenue anticline beautifully by just looking where those offshore oil rigs are, okay? Because as it turns out, anticlines are great oil traps, okay? In fact, this is what most geologists who work for oil companies are structural geologists who know how to find anticlines, because that's where the oil is, all right? Okay, what that means is that along the limbs of those sorts of structures, or even if we have the San Andreas Fault sliding more or less smoothly along, there's always a vertical component as well. It's never usually purely horizontal movement. So at various rates along the coast, we have uplift going on, as well as sea level going up and down, okay? And that complicates things. In the early days when people studied marine terraces, earlier on, people said, well, I think it's all due to sea level fluctuations. And then other times they said, oh no, it's all due to uplift. You know, and you get uplift at various times and terraces get moved up as a result of that process. It turns out it's actually both. In most parts of the coastline, these tectonic processes, such as uplift, take place at relatively constant over the long term and gradual rates, or more or less continuous kind of thing over time scales of thousands or tens of thousands of years. So sea level fluctuations are superimposed on that steady and more or less constant uplift. So what we see preserved on coastlines is a series of marine terraces that correspond primarily to our interglacials. Here's the present one forming, and then during a past sea level, the last interglacial formed a terrace, but it was initially exposed when sea level lowered during a glacial, but then when the next interglacial came, uplift carried it up out of the way, okay? And that happened with all these others as well. And so primarily what we see as a series of step-like landforms called marine terraces is a record of interglacial periods, okay? Now, do terraces form during glacial periods offshore? They certainly do. And K.O. Emery from Scripps Institute of Oceanography mapped all of those on the Channel Islands back in the 1950s. And there's a series of submarine terraces off of all the Channel Islands and off the mainland coast as well. But those usually don't get uplifted because they start out way below present sea level. So it would take an awful lot of uplift to get those up and exposed so that we could see them today. And oftentimes they get eroded before they ever get that far. So again, most of what we're seeing here is a record of interglacial periods. Okay? And the Channel Islands have beautiful records of them. Here's one of my favorites. This is San Clemente Island, and the last interglacial marine terrace is this one down here, this big broad one that the road is on. The interglacial before that is this one. The interglacial before that is this one, and so on. San Clemente Island has at least 20 of these, and they may go all the way back to 2 million years or so ago. They're way beyond what we can actually reach with our dating methods, or even where we can find fossil material that might be suitable. But Channel Islands National Park has good records of these as well. And we can see good records particularly of what we think is the last interglacial marine terrace. One of them in particular is here, is on Santa Cruz Island, and there's good exposures of this on the southern part of the island, down here at Johnson's Lee, over by Forney Cove. Nick Pinter, who was a student at UCSB, mapped these. He sent us some corals, and we dated them, and sure enough, they date to the last interglacial period. And it looks like right around a lot of Santa Rosa Island, there's a really good bathtub ring of the last interglacial recorded as a marine terrace there. Same thing with San Miguel Island on the southern part, and over here on the northwestern part as well. Poor little Anacapa doesn't seem to have anything from the last interglacial period, but have you ever noticed how nice and flat the tops of east and middle Anacapa are? And that if you trace that around, there's sort of a bench-like feature over on west Anacapa? Marine terrace. We think that dates to an earlier interglacial that we hope to try to get an age estimate on some point in the future. But the last interglacial seems to have been eroded away on Anacapa. But here's what they look like on some of the other islands. This is on Santa Cruz Island. This is the Johnston's Lee area. There's that last interglacial marine terrace. There's an older one right up there, and a still older one up through there. Nick Pinter mapped 3 of them here. On Santa Rosa Island, as you approach the island, as you're going into Bechers Bay, this landform that you see right out here, this nice flat surface, is a marine terrace that we think probably dates to the last interglacial period. At least it's a very good candidate. And there are remnants of an older one up here, and again over up here. Anytime you see these flat mesa-like surfaces, that's a good clue you're looking at a marine terrace. San Miguel Island has some beautiful ones exposed in Kyler Harbor as you're entering, and we think this is probably one that dates to the last interglacial period. And it's over on the other side of the harbor, right over here. You can pick it up as this flat surface. It's mantled by a bunch of landslides here and by a bunch of dunes here, but you can see that nice flat terrace-like morphology or form that is so typical of marine terraces. And even little old Santa Barbara Island has 6 marine terraces, 1 square mile, and it's got 6 interglacials recorded on it. Isn't that phenomenal? That's why it's a national park. It's got stuff like this. Now, one of many reasons it's a national park, I should hasten to add. But at any rate, here's our best candidate for what we think is the last interglacial terrace down here. And these are sediments that have been dumped on top of it. Some of them are marine sediments in the lower part, sands and gravels with shells and other sorts of materials. And some of them are materials that have obviously come from down this slope. You can see them being actively moved down there even as we speak. But there are higher terraces as well. And you can see them in through here. This arch is pretty soon going to remove a lot of this one so that it's just left as a C-stack. But we have an older terrace here and still older one farther up. So we have beautiful records of marine terraces and interglacial periods on the Channel Islands, some of the best in the world. Now, how do we determine how old these things are? It turns out that with things that get beyond the range of radiocarbon, the preferred material for dating, which will take us into a technique that takes us farther back, called uranium series dating, and which can best be used for marine terraces, is coral. This works great for coral reefs in places like Winley Key, Florida, or Puerto Rico, or Playa del Carmen, Mexico, or Barbados. What are we going to do here? Well, fortunately, we do have a coral that lives off the west coast. In fact, it lives from central Baja all the way up into Alaska. I've actually seen it in the intertidal zone on Prince of Wales Island, Alaska. So it's the orange cup coral, this pretty little thing here. And if you've ever done any diving offshore, sometimes you can see it. It's on rocky intertidal sorts of coasts at relatively good depths. It's not found intertidally here. You have to get up to about Oregon or so to find it intertidally. Here it is as a close-up of a single individual. And in fossil form, when the organic material has decomposed away and we're just looking at the hard parts of the skeletal material, this is what it looks like here. There's a pair of them, but they aren't colonial. They're actually solitary corals. Okay, they're solitary individuals. But as far as dating is concerned, it doesn't matter, because it turns out that corals, whether they're solitary forms, whether they're big colonial corals on the Great Barrier Reef of Australia, all of them take up uranium from seawater, a little bit, about 3 parts per million. And they do this because ocean water has about 3 parts per billion uranium in it. It turns out the ocean is actually the great reservoir of uranium. Who would have guessed, huh? It's not very concentrated, so you don't have to worry. You can go swimming. You won't get any kind of a significant dose or anything like that. But it is cumulatively a big reservoir of uranium, simply because the ocean has such a large volume. A key thing to remember here is that it doesn't contain any thorium. And it turns out that an isotope of thorium is the first decay product, the first long-lived decay product of uranium, okay? But ocean water doesn't have it. And so when corals take up uranium from seawater, they don't take up any thorium, even though they do take up a little bit of uranium, okay? So it takes up the parent and no daughter. So it starts out with something that's going to decay away, but there's no daughter there to begin with. Now, no other organism does this in any significant amount. Hydrocorals take up a little bit. Calcareous algae takes up a little bit. Echinoids take up a teeny bit. The most common fossils in California marine terrace deposits are mollusks, and they do not take up uranium from growth. So we've got to find corals. And you saw how tiny those little guys were. So what this means is when you go to a fossil site, it means lots of sieving. So you sit there and sieve and sieve and sieve and sieve, and finally you can pick out a little coral here and there. They're hard to find, but they're there if you keep looking for them. What's interesting about this is that we have not only uranium-234 decaying to a thorium isotope, so we start out with 0 of this and 3 parts per million of uranium that decays away, and this builds up then some thorium over time, and that gives us 1 clock. But it turns out that we also have, since we have more than 1 isotope of uranium in seawater, and uranium-234 actually is in a slightly greater activity than its parent, uranium-238. And it starts to decay away. And so it starts out with a ratio higher than 1 and goes down to 1. This starts out with a ratio of 0 and goes up to 1. You don't need to remember all this. Here's the important thing to remember. We have 2 clocks in the same coral, okay? That means that this is an unusually robust dating technique because we can check ages here against ages here. And when we get good agreement, which we sometimes do, and sometimes we don't get them, but when we do get agreement, we have a very high degree of confidence in the ages. This is something you don't have with radiocarbon dating, you don't have with potassium-argon dating, a lot of other dating techniques. So this is something unusual with uranium series dating, as long as you've got corals that take up uranium from seawater. So this makes it a very powerful technique for dating marine terraces, whether we're in Florida or whether we're in the Channel Islands. Okay? All right. So let's go back to our oxygen isotope curve. Again, the deep sea oxygen isotope record suggests that we had a warm last interglacial that was only about 5,000 years old, or 5,000 years long, from about 126 to about 121. In this period right in here. What does the marine terrace record say about that? If we look at what we've been doing here in California, on the Channel Islands and down in Baja and some of our mainland localities, we've found enough places now where we found enough corals and where we can date a lot of corals, we can start to see what the range is for that interglacial time period. And it turns out that it's kind of interesting compared to the oxygen isotope record. Remember that one was supposed to start about 126 and end about 121. Well, on San Nicolas Island, looks like it actually started about 121 and ended much later. Same thing on the Palos Verdes Hills, about the same amount of time, and actually maybe ended a bit later. San Clemente Island, maybe starting about the same time maybe as the oxygen isotope record, but going much later. Punta Banda and Baja California, about the same. And Isla Guadalupe off Mexico, about the same. So what we're looking at here is a record that is a little bit later start time and a much later end time and a high sea level that probably lasted at least 9,000 years based on just the ages of the corals. But what has to happen first before those corals get deposited there? First, you got to cut a bench, right? And that takes time. So what we're actually dating when we date marine terrace corals in California was we're dating the latter part of an interglacial period, not the whole thing, just the latter part, because the first part is occupied by a period of bench cutting. And very little record is actually preserved of fossils that might have been living at that time. So this is a minimum estimate then of how long the last interglacial might have lasted. But even with that, we're looking at least 9,000 years or so. Much longer than what the deep sea record indicated in that previous slide. Okay, if we go to someplace like the Caribbean, we have a whole different sort of animal, literally. In this case, we're talking about colonial reef corals. Some of them How many people have ever been diving or snorkeling in the Caribbean or off Mexico? What's one of the most famous and beautiful sorts of corals? The elkhorn coral, right? That one that forms the things that look like elk antlers, elkhorn coral. Acropora palmata is what it's called, and it is one of the fastest growing marine organisms in the world. It can grow really fast, and it can keep pace with a rising sea level. Okay, that's a key thing about it. It can actually keep up with sea level as it's gradually rising and build a reef higher and higher. Okay, that's the most common sort of coral that has been dated in most parts of the Caribbean down through here, from the Bahamas all the way down to Barbados. Now, in some places where we've dated them on Bermuda and Puerto Rico and Curacao, we have records that look sort of like what we see in California, although the start times are a little bit earlier, notice. But in some places where we have unusually well-preserved corals, and many of them, such as the Bahamas and Barbados, the ages range from 130,000 down to 110,000, and in the case of Barbados, way back to almost 136,000 to 116,000, okay? So here we're looking then at records of last interglacials that probably record most all of the last interglacial cycle, because we're not having to cut a wave-cut bench to start out with during the early part of the high sea stand. The coral reef is keeping up with it, okay? So it's recording everything. And if we take the maximum estimates for this, we're looking at interglacial records that last perhaps as much as 20,000 years, okay? At least a minimum of 8,000 years, even these places where we have not such good records, okay? But conceivably as much as 20,000 years. Same thing is true for Western Australia, where there are beautiful coral reefs over on the western part of Australia, in addition to the Great Barrier Reef, which is over on the eastern side of the continent. But here a minimum high sea stand of at least 13,000 years, just based on these localities here where there are last interglacial reefs. And here's one of my favorites, Hawaii. And there are beautiful coral reefs that are preserved here. Much of the city of Honolulu is built on the Waimanalo Limestone of last interglacial age. And this light blue line that you see here marks where the Waimanalo Limestone has been found. These red squares are where we've dated it. And you can read what the individual localities are. But here's the bottom line, literally the bottom line here. A high sea stand that was at least 12,000 years and possibly 21,000 years based on the age of the corals. Okay? So very similar to Barbados and the Bahamas. That's at least 4 times as long as what the deep sea record indicates, and at least 4 times longer than our present sea level has been at its current level. Okay? So our first conclusion, the last interglacial period was long. Okay? Possibly 20,000 years long. Well, if it was long, how warm was it? The way we can do this is by looking at some of the other kinds of critters that we find in either coral reefs that are associated with the coral reef community, or in the case of California, marine terraces that we find embedded in the sands and gravels. This is actually from Cavern Point on Santa Cruz Island. It's an older marine terrace deposit, but you can see a lot of shells all cemented together here. It's a very rich deposit. These are last interglacial fossils from Cayucos, California, up near San Luis Obispo. And you can see it's loaded with shells, okay? And what we can do is we can take all of these shells, identify them all. This is where our LA County Museum colleagues have been crucial in the work we're doing here, and look to see if we have species that live north of us at present, or south of us at present, or is it pretty much the same as what we'd find offshore today? What do we find? Okay, this is what we find, and this is sort of a compilation of a lot of localities that we've studied for a series of species. Here's a good example, a small gastropod called Stramonida bicerealis, and that's the sound it makes when it is migrating northward. It currently lives in the Gulf of California and all the way down into equatorial zones. And you can see it lives up here as far north at present as Cedros Island off Baja California. But during the last interglacial period, it came all the way up here into the southern Channel Islands. We can find it on San Clemente Island, for example. Okay? So it had a migration northward of a couple hundred kilometers here, well, several hundred kilometers farther north, indicating we had warmer waters that migrated north. Same kind of thing that happens during an El Nino at present time, where you get some Baja species that migrate north temporarily, but these did it permanently. Here's another one called Mexicanthina lugubrious. It just barely makes it to San Diego. Well, we find it on Santa Barbara Island, on that low terrace that we think dates to the last interglacial period, and it's found just to the west of here, over near Goleta, in the last interglacial terrace over there. So it made it all the way up here into Channel Islands National Park. Didn't make it past Point Conception, but it made it quite a bit farther north than San Diego. This little guy is one of my favorites. This is Coyote, and a different species of this called Coyote unditella is presently found off Mexico and much farther south, all the way down to Peru actually, and makes it all the way up to about Goleta. But during the last interglacial, it made it all the way up to Tamales Bay. So it thought that Tamales Bay during the last interglacial was just about what Goleta is like now. If you've ever gone swimming in Tamales Bay, it's not like Goleta now. But during the last interglacial period, it apparently was. And a lot of other warm critters like that. And this is another nice one too. Corals. Colonial corals, which we don't have off of California right now, do grow off of Mexico, off the west coast of Mexico, and they're found around Cabo San Lucas. They go a little bit up into the Gulf of California and up around Margarita Island. But they went all the way up to Isla Guadalupe and Cedros Island and farther into the Gulf during the last interglacial period. And these are very, very sensitive creatures. They don't like temperatures that aren't warm enough. So these had to have been warm enough temperatures consistently for these guys to have colonized these northern areas. Okay? Bottom line then, things were warmer during the last interglacial period all along the California coast, and we can see this effect even up into Oregon. Okay. We can also see it in the tropical Pacific. Remember the Waimanalo Limestone? It has critters that don't live there now, such as this guy, Lambus chiagra, which is found in the core Indo-Pacific region through here and along the Red Sea where it's warmer and so on. It migrated thousands of kilometers up to Hawaii. So did this guy, Strombus mutabalis, this guy here. Again, found in the Indo-Pacific and in the Indian Ocean and up into the Red Sea, but not Hawaii at present. During the last interglacial, it took about a 2,000 kilometer trip farther north and had to be warmer waters for it to do that. And in the Atlantic as well. Remember the Rocky Bay Formation of Bermuda, last interglacial age? A lot of things that are just found no farther north than the Florida Keys or the Bahamas migrated up into Bermuda. So that means we must have had a stronger Gulf Stream that was reaching that part of the world during the last interglacial. Things like the West Indian top shell, this guy, migrated up there, doesn't live there now. They've tried to grow it there, dies, won't live there. Grew there just fine during the last interglacial. So did this brain coral, which doesn't live up there now. So bottom line again, the last interglacial was not only longer than what we've had so far as an interglacial, it was a lot warmer. Okay? How high was the last interglacial sea level compared to present? One of our best places to look at this is not Ventura, California, okay, or any place along the California coast. And why? Because we have uplift here. So when we see a marine terrace, we can't say that's a high water mark that's actually marking how high water was. That's a high water mark that marks how high water was plus the amount of uplift it's experienced, right? Because we're tectonically active and we're getting uplift. That's why we've got multiple marine terraces. But places like the Florida Keys and the Bahamas are far away from the plate boundaries like the San Andreas Fault that create this uplift and tectonic activity. So these are places where we do truly see good high water marks. The west coast of Australia is also in that category. The Yucatan, places like that. They're far away from plate boundaries where we have tectonic activity. So let's take a look at some of these. Remember we looked at the Florida Keys before, and these are areas where, since we haven't had any uplift, but we have well-preserved corals, we can tell how high sea level was. Here's a good example. This is the Key Largo waterway. Cuts right across Key Largo, so you can get from the Atlantic over to Florida Bay in your boat. And what you see here is a waterway then that is at sea level. So there it is, sea level, 0 meters. The top of this reef, which is what this is the Key Largo limestone, has beautiful growth position corals in it, like this Montastria and like this brain coral, Diploria. They're sitting right there. That's right where I took these photos, right there. Okay, so they are about 3 meters above sea level at present. Okay, but these guys have to live in water of some certain minimum depth. And it turns out that Diploria and Montastria like water that's at least 3 meters deep. And they even like it deeper, preferably, sometimes 30 meters, 40 meters, even down to 80 meters in some cases. Okay, but let's be conservative and say 3 meters depth. So we've got sea level here at 0. The top of the reef is 3 meters, a minimum water depth of 3 meters. That means sea level in the last interglacial was right about there on that fence line, flooding this condominium backyard by about 3 meters. Okay, so that's our high water mark. So we're looking at a high sea stand about 6 meters higher than present. Okay, now 6, that doesn't sound like a very big number, does it? So you think, well, gee, especially here in California or Colorado, we think 6 meters. Come on, that's about, 20 feet. Is that any big deal at all? Well, in places, it is a big deal. But first, before we get to that, where would that come from? Where would that additional 6 meters come from? It turns out that there's pretty good estimates of what the sea level equivalent is from a lot of our ice sheets. And here are 3 possible sources, actually 4 possible sources. The largest amount of water tied up in ice at the present time is the East Antarctic ice sheet, shown here on the satellite image during an ice aurora australis, as a matter of fact. And this big ice sheet can contribute up to 65 meters of sea level rise if it all melted. But it's a fairly stable ice sheet. It's been there for a long time. It's not as sensitive to climate change as this one, which is the West Antarctic ice sheet. It's partially grounded underwater. It has a kind of inherent instability and is quite sensitive to climate change. It can contribute about 8 meters of sea level rise, which is about the same as what Greenland can contribute, about 7 meters of sea level rise. If you add everything else up on the Earth, including the relatively big ice caps on Iceland here, all the mountain glaciers in Alaska and Canada and Scandinavia, all of those put together, 0.5 meter. That's about it. Okay? So that's not much of a player. This one is fairly stable. This one and this one are the main candidates that are potentially the ones that could contribute to a sea level rise. Okay? And both of them are potentially unstable. It is some combination of these, all of Greenland perhaps, or most all of Greenland, or most all of the West Antarctic ice sheet that created that 6 meter sea level rise, or maybe half of this and half of this, or a third of this and 2/3 of that. And there's a lot of debate about what the relative proportions are that could have caused that sea level rise. It does look like from the most recent cores that have been taken on Greenland that there was some last interglacial ice preserved. Not a lot, but some. So my guess is it was partly Greenland and partly the West Antarctic ice sheet that were the contributors to it. So does that matter? We're talking about a few meters. Is it a big deal? Here it is. Take a look at these cities. Now these don't sound like little podunk cities from my way of thinking. Miami, Fort Lauderdale, Palm Beach, Cape Canaveral, Daytona Beach, Jacksonville, Tampa, St. Pete. These are pretty big cities, right? Okay, during the last interglacial period, this coastline of Florida looked a whole lot different. In fact, it looked like that. Here's the outline right here of modern Florida. And what happened to all those cities? They're underwater. They are underwater. In fact, last interglacial deposits called the Miami Oolite are what the city of Miami is primarily built on. Okay? Same thing around Tampa, St. Pete, Cape Canaveral, goodbye to the space program. Daytona Beach, goodbye to the races and spring break. Jacksonville, you name it. There's all kinds of problems here. And this isn't the only place. If you look at other countries like the Netherlands, Bangladesh, how about Washington, D.C.? You know what would happen to Capitol Hill during the last interglacial? It's an island, okay, surrounded by a moat, which has been a suggestion that some people think it maybe really is, okay? At any rate, conclusions, and thank you for your patience getting through this interglacial length discussion. The last interglacial period was long, at least 9,000 years. We know that just from California. We know that's a minimum figure. Based on what we see in other places where we have better records, possibly as long as 20,000 years. Thus, we may be many millennia away from the end of the current interglacial period. The last interglacial was warm. There were major range shifts in marine organisms in the equatorial Pacific, the eastern Pacific, the western Atlantic, and elsewhere. Mediterranean, for example. West African species migrated up into the Mediterranean, went all the way into Spain, France, Italy, Greece, even into the eastern Mediterranean. Australia, a lot of the warmer species in the equatorial regions migrated south. The range of coral reefs went further south, and so on. And the last interglacial sea level was high, probably at least 6 meters above present, and therefore a future high sea level of this kind of magnitude would inundate many coastal cities in the USA and throughout the world. So we're looking at impacts that would affect a lot of people, since we have a lot of people living in coastal areas. So this answers an important question. Could sea level ever get that high? When you saw Waterworld with Kevin Costner, anybody see that? Anyone care to admit that they saw that movie? All right, there's a few brave souls. Okay. At any rate, you think, well, geez, this could never happen. Well, actually, sea level couldn't get quite that high. But as far as effects on major cities are concerned, yes, it could get high enough to have a major effect and a significant impact. Okay? So this is the kind of lesson that we want to try to keep in mind when we're looking at future warming. We haven't even talked about what the effect of CO2 is on this kind of thing, but I can tell you right now, we do have good records of carbon dioxide from ice cores, particularly from Antarctica, and we know now that CO2 level at present is much higher than it was during the peak of the last interglacial period, much higher already, okay? And could be quite a bit higher in the next 100 years or so. So I'll leave you with that, and thank you very much for your kind attention. Questions? Where not to buy land in Florida?
What do you think is accounting for your difference in the estimates for the interglacial period based on the Foraminifera?
For the duration? Yeah. The estimates are based largely on this theory about what causes the cyclicity of glacial interglacial cycles. And that's something called the Milankovitch hypothesis, or orbital forcing theory. What the deep sea record has done to estimate the last interglacial period, it's actually not directly dated in most of the cores, because most of the times we're way beyond radiocarbon dating. We don't have corals in these deep sea cores. We just have little forams. They're going either on settling rates, but the other thing they're doing is using this orbital theory and actually calibrating the oxygen isotope curve to the orbital forcing, which can be done by celestial mechanics calculations. To be honest with you, in my view, it's kind of the tail wagging the dog. There's some circularity in that. But that sort of a method estimates the last interglacial as being a fairly short period of time. The problem is, it is an estimate that has some circularity of reasoning in it, and that's why we've actually presented a challenge to this. And a lot of the deep sea community doesn't buy it, but we think this is sort of hard empirical kind of evidence, and it's not theory dependent. Does that answer your question?
Yes.
Okay. Other questions? Yes, sir.
We've been hearing or heard some about the uplifting areas, like on the eastern Pacific. How does that rate kind of agree with the water raising at the same time?
Oh. During the end of a glacial period, when ice is melting, sea level can rise much faster than uplift. A lot of times uplift can be relatively jerky. It can be, a small amount in a short period of time. that cumulatively over time amounts to a fair amount of uplift. For example, during the Good Friday earthquake in Alaska in 1964, a part of the Wavecut Bench forming in southern Alaska actually emerged overnight. It was a Wavecut Bench one day, it was a marine terrace the next day. And it was an earthquake-generated uplift, what's called a co-seismic uplift. And there was a guy, some poor guy, who was moored offshore who actually filmed it. I'm sure I'd love to see this film. I've heard about it and I've never seen it, but if it would have been me, the camera would have been really shaking at the time. But he actually saw some of this uplift taking place. But that was a good example of the kind of thing that can happen. You actually have some examples of it here in Ventura County. How many people have ever driven up the Coast Highway and gone around Peaches Point? Is there anybody who hasn't done that? You're driving over a marine terrace that's a couple thousand years old. And around Muscle Shoals, that area too, okay? Yeah, that's... Some of those weren't there when the pyramids were built. So that's how rapidly uplift can take place around here. I'm not trying to scare anybody. It's not a problem in Colorado. We have other problems in Colorado. Anyway, I'm not sure if that answers your question or not, but okay. Other questions? Sounds like there's a question here. Is there a question here? No. Okay. No. Okay. Crystal clear. Kate.
Well, if you're thinking that we can predict the length of this interglacial based on the last interglacial, then that means that there's something that's forcing the cycle that makes you think it's somewhat going to be regular. What is driving us to always be going through the cycle?
That's this orbital forcing theory that I was alluding to with her question. Is anyone familiar with that? The idea here is that changes in the Earth-Sun geometry have a tremendous effect on climate change. Right now, we have an orbit around the sun that has, if you were to look at it from up above the solar system, looking down on the plane of the ecliptic, the plane that all the planets are orbiting in, if you were to look downward at the Earth's orbit around the sun, it has an orbit that is sometimes fairly circular and sometimes fairly elliptical, okay? And that changes over time. Second factor is the Earth's axial tilt. Right now it's tilted from the vertical, from the plane of the ecliptic by what? 23.5 degrees, right? That's where our tropics start. It's 23.5 degrees latitude north and south of the equator. That's because of the axial tilt. But that tilt actually changes sometimes. Sometimes it's 22, sometimes it's up to 24. It goes back and forth. That's cyclic too. Okay? And then a third thing, the precession of the equinoxes. Right now, our northern hemisphere winters are when we're tilted away from the sun, right? But we're actually closest to the sun in our orbital path. In our summers, we're at our farthest point away from the sun, but we're tilted towards it. And it's the tilt towards it that makes it summer. But that changes through time, and there are times that during our northern hemisphere winters we're farthest away from the sun, and at perihelion, when we're tilted towards it, we're closest to the sun. So we have increased seasonality as a result. Colder winters, warmer summers. Okay? Well, when all these things combine, and they have cycles of 100,000 years, 40,000 years, and 20,000 years, but when all of those things combine so that we have a minimum of solar radiation in northern hemisphere latitudes on the continents in summertime, that's when we can grow ice sheets. Because that's when we're getting less radiation at those latitudes. Ice sheets can build up over the summer from snow that's fallen in the winter. And when the reverse happens, and we maximize the amount of solar radiation in summer at those high latitudes, that's when we melt them. But because of the cyclicity of these three orbital parameters, that's what drives the cyclicity of the glacial interglacials. Okay? That's called the Milankovitch theory. And Milankovitch came up with this in 1941. And it wasn't established as being an important part of the process of Earth's climate change until the late 60s. And then we first started with uranium series dating and started seeing that there were some correspondences between what Milankovitch would have predicted. In fact, Somebody once told me a story that Milankovitch was on his deathbed when the paper came out in Science that established this, and he breathed a big sigh of relief and a smile and then died. But I don't know. It just sounds a little too true, good to be true. But at any rate, had that happened, I'm sure he would have smiled and died happily. But the problem is that, and I should point out, what causes this change is the gravitational effect of other planets on the Earth, okay, and how the planets are lined up, particularly Jupiter, since it has the largest mass. So you can actually calculate these orbital factors, and they've been calculated 5 million years into the past and 5 million years into the future. And in fact, I just sent a guy a copy of the whole thing. Took one Excel file that was about 20 kilobytes that has the entire Milankovitch cycle for 10 million years. 5 million into the past, 5 million into the future. It's all been done, not by me, but by celestial mechanics folks who can do these sorts of calculations. But that is the cyclicity that's the basic driver behind it. Here's the problem. Other kinds of things enter into climate change as feedbacks. One of them is carbon dioxide. Another one is dust and its effects on radiation transfer in the atmosphere. That's what a lot of my current project is built around, is trying to understand that. And there are other kinds of factors as well. These complicate the issue and make it less of a predictable kind of thing just from the Milankovitch properties. So that's why it's complicated. Yes?
That's what I was going to ask you. Given all of those factors that you talked about that are cyclical in nature, what's the role that we're playing in terms of carbon dioxide and those issues? Is it really significant in the long term?
Yeah, it is. It is significant. We do see that carbon dioxide does track the Milankovitch cycles. We don't know exactly how that happens. It's still not well understood. But CO2 levels in the atmosphere are low during glacial periods, like 180, 200 parts per million volume. During interglacial periods, about 280 to 300. Well, we're way above that now, and we're steadily going. Has anyone seen Al Gore's movie?
Yes.
Have you seen his CO2 plot and how it compares with the last 6 interglacial periods? Yeah, it's a huge difference. It's unprecedented. It goes beyond the last 2 million years of geologic time before we can find anything that's even close. You have to go all the way back into the Pliocene, which is prior to the whole glacial interglacial cycles that the Milankovitch theory has moved along to drive. So we're moving